we have installed the mini conda, right? And then once you install the mini conda, this kind of Python environment system, and you will have to start from here. So we install Miniconda, and now we have to set the environment, because in the Miniconda you can set lots of different environments. I usually do like a 2 hours sessions for this Jupyter Notebook and Python language, because we used Python scripts, and Jupyter Notebook is one of the IDE, which is in develop integrated development environment. But because of time, we can search maybe mini conda. Yeah, here. Well, I can type anaconda, yeah. And then you will see this kind of the comment, anaconda prompts, and click it. And then you might see here's the base, which means we only have one. This is kind of default environments once we install the mini conda. And if you have already like Python or the Anaconda environment, you can just skip this step for setting another environment. But if you have mini conda and install today, you can type conda update conda, and it's going to just check your library has been updated in the base, and then click process type yes, and then it will automatically install all of or update all of the library in the default sessions, default base environment. Done. Now, then we are going to create new environments, your working environments. And I named Apex Path, but name doesn't matter. And you can type this one or just copy. Click by clicking this button, and it has copy. And on this prompt, you can right click it, and we just paste this command. This means we are going to create a new environment, which is n name apex mf, and the base Python package version is going to be 3.7. And we also going to install Jupyter Notebook, because this project, well, these optimizations, we need the PyMu, which is the one of Python language developed by USGS, and that help you to, work with the past utilities. And also Flowpy. Flowpy is the package for Modeflow. So that's why I just keep it just Python 3.7, although we have like Python 3.9 now. Then just type enter, and this asks you really want to create a new environment, and then I will say yes, and the type Y, and it's going to create new environment named Apex Path, and install like basic Python version and Jupyter Notebook. Any questions so far? Okay. And the reason why I'm showing this, sometimes we have to consider your integrated model optimization, but there's a way. And once you familiar with little this, Python script, well, Python script with Jupyter Notebook, then it's reproducible. You can apply this one to any other watershed Apex modular model. Now we just create new environments, and this time we have to activate this Apex past environment. So there's a way, Conda, please activate this Apex MF past, and then check this button and the copy. In the same way, you can right click on your mouse and enter. Now this activate environment has been changed to Apex MF past. And then I developed a Python package called Apex MF. And I unfortunately I'll have to update it this Apex MF yesterday too. So if you have a Apex MF library already, you can use this pip install. Well, U means upgrade. And then if you don't have it, you can just copy this and then paste and install it. So this is the Python package I'm working on. Yep, here we go. And the latest version is 0.1.3. And if you have some knowledge of the Python, you can be contributors of this, package. And also, if you whenever you use this one and find the bug, you can go to, I put it somewhere. Here's a bug tracker, and then click, and then put your issues here with your, the bug. But you should have a GitHub account to do that. It's not hard. Yep, we install all of the Apex MF package and dependencies. Then let's go over to this. And we just did it. Here's pip install Apex MF. And also we need to have the data. I call it animus journal calibrations. And here's a notebook we have to work on. You can click this download link to download all of these materials. And there's another way. If you have a GitHub, you can just clone this material and then copy this copy this command into your git bash terminal or any other environments. And then here's instructions how you do it. Let's download this material. It's about 20 megabytes. And open it. It's in the download folders, so you might just put it and go to Album, put d03 sessions. 2, 3 seconds. and paste here and unzip it. Extract. Okay, now we have these folders, and you have info file, which is an Apex mode flow info file, and here's a notebook that we are going to working with. So once we the first decision, we create the Apex mode flow RT3D, and then it's the same data set. So you can bring in it and then do the same. The one thing that is different, we didn't have set in the first decision, we didn't set any your journal parameterizations. That can be done by by manual or using graphical user interface. And I'm going to put it this function too later. But what it does for the mode flow parts, we have one package more. I guess two package more, which is okay. The value, your parameters name, which is HK hydraulic conductivity 1, 2, and specific yield, and has the value. And another one is your John package. John package contains informations where you have this John. So HK1, you can see here's that one flag. And this is really hard to do by manual. And there's a way that we can do using graphical user interface too. Okay, then we got this data sets. Next step is open, well, you can change the directory, such as you can, if you have this data set, you have to go to D directory, but we don't have D directory or E directory, yes. And then you can open up the Jupyter notebook. But if you have the data set in the C drive, you don't have to go anywhere, and then you can type the Jupyter notebook here. Jupyter notebook. Because I do have a data set in the C drive in the data desktop. Now you will see you have new window web browsers, and you can see the some folders. This is in the C drive, and I will go to desktop and go to data day 3 second sessions, and here's Apex MF OPT main folders, and here's notebook. And notebooks, you have intro to past and journal setup and journal run. So let's just briefly overview over the introductions to past. So once you click, yes, it is. I didn't mention anything about who built it, but we are going to do this here. So the question is, this is the past model independent parameter estimations developed by Dr. John Dorothy. Yeah, that's right. So USGS and then Dr. John Doherty and the watermark companies developed this past tool. And usually these past utilities has been applied like mining field. And in the mining field, we also need groundwater model. And there are lots of uncertainty. So he and then his colleagues developed these past utilities to optimize groundwater module. And there's really nice. I mean, once you open up this one and you can click this button, and then now you're still this PDF has been downloaded your computer, and then you can. This is one of the great manual, and this is textbook how groundwater modeling can be optimized and then analyze these uncertainties. And the groundwater models, they don't really care about uh, calibrate value. They only care about, well, many scientists from there, they care about the uncertainties. And then these three books talk about more of the uncertainty analysis, how you can reduce your uncertainty on your hydrological responses, such as groundwater table or the groundwater qualities. And by doing that, the PAST is really nice tool. Um, it's kind of really tricky to prepare the inputs and do the analysis, because um, this also written by Fortran, but PAST plus written by C++, and all of the inputs output is just the text format, ASCII formats, and it's really hard to do by manually. But using this framework, I hope you guys can have follow easily. But this also we need some kind of Jupyter notebook knowledge and the Python knowledge too. So that's one trade-off. So basically, past algorithm. In the search algorithm in the past, they used Gauss-Levenberg micro algorithm. And the central feature of the past engines, this search algorithm iteratively optimized your model parameters and to improve its fit to observe the data in any other object. And the measurement objective function can be, left pi, the left term is equal to the weight sum of the square of the residual between measurements and simulation result. And there are two major driving forces beyond this algorithm. And, because these days we have, neural network machine learnings. And this Jacobian matrix and the covariance matrix has been getting famous again, because this neural network machine learning is using same this matrix. And so for the Jacobian matrix, you can read about this little descriptions. And so first, they used this Jacobian matrix and do the parameters upgrade vectors, and the parameter upgrade vectors has two different methods. One is gradient descent, and another one is the Gauss-Newton method. And based on this lambda value after each iterations from the Jacobian matrix, they choose what kind of method they have to use. This is especially we have to understand, because apex mode flow is not nonlinear model. It is nonlinear behavior model. So because we cannot just define the linear correlations and define optimized high objective value, we will help to use like different methods to follow this nonlinear optimizations too. Okay, let me just, quickly move on about this kind of the concept of the past, because I think I have some informations. I put this one here. Where is it? Okay, I think I missed. Yep, let me just type it. Past, .org, something, I don't know. Oops. Past, or yep, this is the one site, and there's lots of the book or tutorial education video. You can read it, and then get some of the, you know, knowledge of this past. Okay, then let's move on to. So mainly the past needs three different files, and what this past this framework does, I this manual trial and errors with the past, you don't have to do it. This is kind of automatic parameter estimations, and it says pre-processings can generate all of the necessary file, and post-processing you can extract your simulate value from your model. So we need the template file, instruction file, and also control file. And then once we run this past optimization tools, we can calculate the sensitive coefficients from the Jacobian matrix. And this is not the global sensitive analysis, but usually sensitive analysis, uh, in the ground part, we don't do this sensitive analysis to filter out some of the parameters. But while in the past framework, while optimizing this model, they create the Jacobian matrix and find out most kind of parameter identifiabilities analysis, and then put it important parameters into more forward arrays, and then we call it like a singular value decompositions. And I hope I can cover this subject later too. Okay. So, Jehak, do you have something to say?
Oh, no.
Okay. So we have 1 hour more. So I said this framework, I just include a journal approach instead of pilot. Pilot approach, you need another geostatistic analysis too. So I put it animus river, and then divide two zones. And two zone makes a two hydrogen conductivity and two specific yield parameters. And grid size is 1,000 by 1,000 meters, and 76 columns and 131 rows. And then you can see we have blue zones and red zones. And by the way, this is the modem use. In the modem use, you can easily create this mode flow model. And then the mode flow model you create by modem use can be easily put in this Apex mode to link with Apex model. So, in the Apex, we have 75 subbasins because animals, and then we assign 6 parameters. Yes, here's you can have different spatial parameterizations, journal approach, Pinto approach. My original Animas watershed have these pilot points, and you can see based on this pilot point that they have different parameters that is interpolated by these points. But the journal approach on the left, you can see the sum of different zone, and this is kind of regional regularizations by your hand, and this kind of can create a high uncertainty too. In the river cell, we know now riverbed conductance and riverbed thickness can be your important parameters. How to contribute your groundwater to the streams, right? Then you can assign this to as journal approach or pilot point approach. This is framework. I think I've been covered this one during this break. So we want to run the past, and we cannot do well by your hand. It takes really time, and to understand also it takes time. And then this text format in the Fortran, the characters of the Fortran, once you have you missed one of the line or space, that has to just crash. And this is the template file. You have to manually change this value and go to create the template file for your parameter and change this value in the past delimiter symbol. And this PALM 15.0 date file, and here's template file. If you want to use these parameters, go there and then change this value with to this past symbol delimiters. There's some rules how to construct your TPL template file. Here's the instructions, and instruction file is going to take care of your observed data and target value, such as we have a stream flow output from subagent 75, and this is monthly, and I want to match this simulate value to the target value because I have observed the data for 75, and then you have to change the name like this. And this is really cumbersome and tricky, and it causes lots of errors. And I do have now monitoring well, but I'm going to optimize depth to water instead of the water table. And here's rules for instruction file 2. And yeah, we created, and then we have to run. If you do by manually, you have to run it and then change and modify the info file line by line again. So next one is going to be setup. Once you click, you will have another Jupyter notebook. You can go back to the original one, the previous one, and go to File menu and close it. And go back to Animas John setup. So once you install the Apex MF package, we have to check the version. But before we do it, we have to understand that this Jupyter Notebook IDE functionality a little bit. So we call it this is the cell. They have different cell, and the cell can have scripts and markdown. The markdown is also code, but it's not the code the script we need to run. And this is kind of notes on your Jupyter notebook, the memo. And this, the script cell, this is where Python script, Python command is going to be read. And you can save these buttons. Here's the save button. And also there's, lots of different menu, but we usually click the cell and then run it. And as a shortcut, you can do Shift Enter as well, and it's going to run this cell with these scripts. And because I want to check this Apex MF versions, and this is the latest versions. If you don't have this 0.1.3, you better upgrade your Apex MF Python package. Now you can run it as we set up. We are going to calibrate this Animas River watershed, but the simulation period, because this is practice, so I'm going to put it just 1 year with no warm-up period. So it's going to be 2002 and 2002, but it's 1 year. Yeah, January to December. And measurement data we have is, we have all the stream flow discharge from 3 different locations, but the water table is really varied. And the calibration validation period you can set up, but I'm going to do the same period as the simulation period. And Apex parameters is going to be this one from POM file, and I will let you know how to set up this. And multiple parameters, like I said before, this is journal approach, so we have only 4 parameters this time. Okay, this is kind of initial settings. WD is your working directory, your model folders. So what I have here is these folders, Animas journal calibrations. You can just copy this path to the here, and you can replace it. Okay. And one thing I want to talk about is Python doesn't like 1 backslash. So you have to give it double backslash. Yeah, we set it, and this is going to be your mode flow folder, because we have multiple folder here too. And we have to assign your rich file. Rich file is the site 75 rich file. And then I've been trying to optimize the crop parameters too, but this time I'm not going to cover this, only stream flow and water table. And you can say a simulation start date is going to be January 1st, 2002, calibration January 1st, 2002, and end dates. I assigned it, and this is going to be monthly average stream flow. So timestamp is going to be month. And this is sharp button is coming out. So Python is not going to read this one. And also there's lots of functions that we can add, but this time we are going to calibrate stream flow from subbasin 12, 57, 75, and grid ID, which is from the model. Well, I can show you where the grid ID. And here's the DIs. Yeah, this is 131 rows and the 76, and then the Apex mode has grid ID on each grid cells, and I use this grid ID, and we can run it this cell. And if you want to know what this module does, you can just put the question mark and run it. And now it says your argument will be here the Apex working directory and subbasins numbers and grid numbers, and this means the simulate the start, calibration start, and the time step. And we don't use this time leap year index. Can close it. And based on this inputs, we are going to create com file, which is located into your model folders. So let me open up. So it has all the informations. We just put it. And during the past algorithm, past process, they're going to read these informations. And you can also get what they have in the variable. And this is the Apex utils and initial set of functions. And you can also make a question mark, but the argument is working directory. What it does, we are going to copy all of the necessary past info file to your working directory. So we copy and paste this build past executable, past file, and any other utilities, and for the run Python scripts. Let me just zoom out and how this is, this is the script that we need to, create all the necessary file. But I will just go over. And pbel file indicate multiple pbel package, and the farm file is pom 1501 dev file, and we assigned make the variable for this, and this GW par this line is going to create multiple pbel using the multiple pbel and create the template file for you. Now we have template file for this. You don't have to go directly and create a template file and replace this value with past delimiter symbol. And also for the farmdev template file, before we do it, you can open up this Apex parn Excel file. And this is one thing I added. And once you open up, we have all informations. We have all informations of your farm file data. And the first column indicates the farm number. And it is absolute lower, absolute upper, and default initial value that comes from your Apex 15 or this Excel. And then here's the descriptions. And then if you want to use some of the parameters, you can just select Y instead of N. And you can also set initial calibration value here and the low value, upper value. If you don't have it, this code is going to read, okay, you don't have it, and I'm going to use this parameter initial value and lower value and upper range. So you can name it Y. Well, I will just get rid of P92, let's say. Yeah, can I? Oh, I'm not able to do this. Yeah, okay. Yeah. Well, but still, we can use this six different parameters for your fun file. And let's run it. Now we create the template file and then change those value with the past delimiters. So let's go back to check the fun file template file. This is the template file we created. And this is original file with temp fun file. Now you can only see we have the past decimal delimiters that we only selected. So P12, P16, P17 instead of value in the template file. Now we just finished creating template file now. And then now it's time to build the instruction file. And these functions, Apex pass the utils and extract month stream flow. Well, like it says, we are going to extract monthly stream flow based on this rich file we assigned already and sub-basin numbers. And the start, we have to provide the start simulation date and calibration start date and end date. We already assigned on the top. So let's run it. Now we just extracted this STF sub-basin 12, 57, 75. You can go back and define the STF. Let's open up 75. So monthly average stream flow in the 2002. And now we have to create an instruction file based on this extracted stream simulate file using streamflow OVD. And we talk about this OVD file, right? And this time I change the name to month, STF month OVD, and we have this data. You can use the same file that you used for Apex mode and run it. Now this one is going to just make the list, and you have this simulate extractor file. In this time we are going to use these functions as STF OBD file and then convert this OBD file with your simulate file into the instruction file. You can, I made it question mark, which means you can get also informations from the arguments. Let's extract it. Okay, so now we have an instruction file. Same as stream flow, you can have the groundwater and grid IDs. This function we are going to extract your simulate groundwater head based on this grid IDs, and the simulation period is the same. This one, and let me run it. This is just warning message. Now we have simulation output DTW, this number grid ID. We can go to check, and this is going to be here. And because this is depth to water, so this showed the minus. And the mode flow can be monthly observed data, simulated data. And also based on this, we are going to convert mode flow OBD to instructions. And here's a file we created from here, and name it. And also we need to have the information about what observed variable we are going to use it. So this is going to, let's go to OBD. It's in the here, the mode flow folders. DWT. Yep, this is observed data what I have for animals watershed, and this grid number match this observed data locations, and this grid number observed matched with this locations, and also you can put it a minus for the missing data. Yep. But the Python code is going to filter out the missing data and match that. And this is the steps we are going to create a dummy control file based on this template and instruction file we just created. And this is the line, and the dummy past control file, I named any dummy.past. And you can just change in whatever you want, and then they are going to collect all of the informations. I have now the pbel template and this pbel template and actual original data pbel and farm templates and original farm debts and depth to water instruction file, and here's a simulation of extracted file like streamflow as well. So we need to set up a little bit about the parameter range, and this code is going to read all of your parameters based on this instruction and template file we just created. And this pval1 column indicate your initial value, and par low boundary is minimum value of your parameters. This is the range, and then this is the maximum. Now, as default, this is like minus 10 power to 10 and plus 10 times. And we have all the parameter groups name. And this time we are going to change parameter group names by using this folded Python code. And what it does, if we have sy and the parameter name, they're going to change the parameter group named sy. If you have a hk, they're going to change parameter group to hk. If you have a p and the first letters, we are going to change this parameter group to apex. So let's run it. Now we changed parameter groups. And set the parameter range and the initial value. Well, I have a hk only and the sy, and we are going to just run it and just make the set the parameter initial value and upper lower boundary value and upper boundary value. Then this code, the export parameters database to the farm, this means based on this Excel file we just got, and it's going to read these informations and then put up this informations into this database. So let's run it. Now we have the Okay, interesting. Okay, not this one. Yeah, here, this one. Now the apex parameter value has been updated. Initial and the lower boundary and upper boundary. And replace dummy observed data with real ones. And then you can run this code, and we are going to bring up this observed value and the name, and all of default observability now is 10 1.10 plus the power of 10. Then we are going to give different observed group names by using this code, because once we have GW, and this code is going to create observed name, just get this information to here. And for the stream flow, you have different observed name. This is quite nice functions. I mean, once you have different observed name, you can assign the different weight while you optimizing your Apex mode flow. And also you can assign the certainty rates as well. And this weight vectors is really important when you optimizing integrate model. And I will explain this later on. And we are going to import this observed value from this DTW the observed file, and we can see non-value, some of them, and as same as the DTW. DTW means a depth water value, and then we just extract this observed value for this stream flow subbasin 125775. And let's make it. Now we have replaced this dummy observed value with real observed number. Yeah, it's done. All the setup, but it's much better than do by manually. Now we have to set up, lastly, control file, the comments. So before we run like a parallel processing optimizations, we have to adjust the weight on your observed the groups, because let's just think about how about your concentrations and the stream flow. They do have different scale and different units, and by adjusting these weights, you can make all of the observed mismatching value between observed and the simulated value visible to the past. And let's say you have residual between like a concentration residual between simulate observed is like 0.0001, but your stream flow can be like hundreds, and the past only know, okay, your observed residual value from the stream flow is really high, so past just focus on adjusting your parameters based on your residual from the stream flow. And that's the one thing past provide these functionalities to adjust your weight. So I will run it, and it says we have this is kind of iteration number. The reason why I set up, we have to adjust set up at 0, we have to adjust the parameter weight, observe the weight first. And this is number of the parameters we have is 10, and we have observed data points at 49. And we can go this the name any past. This is mode flow forward. Okay, and it passed. Open with the notebook. Now we already set up the control file, so you can just run it. Always run is easy. And we can go back to your folder, notebook folders, and there's this John run Jupyter Notebook. Same thing, you can import library and the set working directory. Yeah, I can just copy from here. And run it. And this line is change the directory to your working directory. And we have the past control name is the case. And to adjust the model, we are going to just run, adjust the weight, we are going to just run model first one time. And now we're running, but let's check. So what it does, it's going to run the model first, and then because we didn't modify the reverse, it doesn't mention about this. So let's wait until the end, because this is 1 year simulation. So run it quick. Okay, as says, we extract the simulate stream discharge and extract the depth to water table for you. And we have these extractions. Now we have some of the scared weight residual, which is called the pi. And then you can see a different group has a different pi. Like I said, we have different units in the scale. And GW98 is really small. And 124 depth to water groups as almost the same as this one, stream flow 12. But once you want to this residual pi from these groups, you can, give it the same weight. So what you can do, get this sum of the scared weights and the copy and put it here. Let's reweight, run it. Now you have another in the command, and let's go back because I named a new control file and it passed underscore reweight RW. You can go to find this one. Oh, okay, not this one. This one with notepad. And once you scroll down, you can see this third column was the one weight one, but now we have different weights for each observed group, so that PAST can read all of some of residual from all of this different group. And this is weight here, this one. And you can combine with your uncertainty rate too. So go back to reweight, and we can run the parallel processing very fast because each iterations, because this is the watershed, we have 10 parameters. So we might need like each iteration can 20 simulations for each iterations. So this code will show you some of the arguments and descriptions. And the one argument is working directory, use your past control file, and number of workers you want to use it. As a default, this code is going to read your computers and find out how many cores you have, and they are going to use all of them. So I just set maybe 10, and then because based on and past no, this is the main folders. So main original folder is not going to be used to this parallel processing, but once you run this code, it's going to create. Sometime it asks you admin request. Well, you can just skip it, this step, but okay. Oh, you should close this exit file because it's going to copy all your original file. And that happened. Let me just restart and delete this one. Worker 1, worker 0. Need to run again. We just need to pass the alpha file variable, and then we can run it. Oops. Okay, let's wait. So there are what it does is going to create the folders for you, like 10 different workers, because Python started with a 0, and now we have 10 different folders, and each iterations. This is the main, and they are starting calculating Jacobian matrix by running more than 10 times. So basically, you don't have to have more workers than your number of the parameter. But if you have 10 parameters, I would suggest like 20 workers to fully parallel processing, because sometimes Jacobian matrix can calculate the forward and the back. And once you have like additional computers, like on the same network, you can use these functions like execute worker. Let me put up kind of, this. There's lots of argument too. First, your working directory and the control file and your main host IP. I hope nobody would hack my computers. This is my, I think, IP. And then you can add the work more here. So the one thing we can do is still be running this 10 times. Let me put this Jupyter Notebook run file, then and the data set we just create and copy to my original computers so that you can see this one. So let's zip it, this one. Can I zip it? I don't have a tool. This. Okay. Okay, so we just finished the first iterations. parameter is now partial polarization and lambda search. There might be another questions. Okay. So what I can do is writing 7G. Download. Yep. Install. Okay. Close it. Scan. 7G. It's okay. It says we're not going to can get the zip file for some of file, but that's fine. We can. And I will put this onto my desktop. Okay. This is my original computers, and I put here. Oh, it's messy. The E drive. My backup. Okay, maybe here. I will name it D3. And then let me unzip it. And we have to bring the run Jupyter Notebook. So yeah, now it's calculating Jacobian matrix 20 times. So here's the notebook here. Notebook. And run it. Oh, okay, here we go. And I will put the Jupyter Notebook here. And I will quickly activate. And you should have this Python ecosystem on different machine too. And this is the C drive, I guess. Yep. And I will activate Apex MF pass and run Jupyter Notebook and bring that up. Where? Okay, here we go. And there was desktop d3 and open the Jupyter Notebook. We have to set another working directory. No. Okay, this is new working directory, and this is much shorter. Okay, double backslash. Run it. Oops, I have to import this one first. Run it, and then we just need this passed out variable because we are going to use the same control file name. But it doesn't matter because these workers on the different machines, the communicates through the internet in the same network. So past is going to control this on the workers controlled by the main past working directory. So this time we are not going to execute the bail past. Instead, we are going to execute workers. But firstly, we have to know what host, what kind of host is. Here's maybe CMD. I hope no one hacked my computer, IP config. So usually IP config gives your IP address, and I'm going to copy this to my original computers. Will be this one. Yep. And yeah, run 10. I'm going to use number of the workers. It's going to be 10. So it generates another workers on your second computers. And then, oh, please. Okay, let's wait. Yeah, it's done. And then now you can see here's another workers 0 to 9. You can set a different ID. But once you go back to your main past, in the main the past command, they realize, okay, we have another worker on the different machine from here, you know. And then this is the slave host. What it called the slave, and open source community changed these slave names to worker recently. So now you can see all of the workers working together. And now where we 20 time, this is second iterations. And also in the zone notebook, there's some linear analysis I want to provide, but I think it's going to take a little time. So how about I just show you this, the line of code to give you a current status of your pi, some of the residual square. So once you run, you know the current pi status. Where is it? The main. No, not this one. I think I have to remove this taskbar. How I can hide? Okay, let's hide it. Nice. Then, okay. This is the main, and we are in the third iterations, and now we calculate the 20 time running simulations. So, okay, and then you can also use this code. You can get the data frame that has measured whole model and residual based on this weight. And also you can get the pi progress plots. I hope working. Okay, it's really small. Let's run. Now as the pi, your sum of squared residual has been a little bit decreased. You know, this data set I create based on the calibrate one, but I gave different spatial resolutions. And also this plot also show your the scatter plots, one-to-one plots for group 98. I don't know why it doesn't have this one. And the stream flow. Here's the 57 stream flow, 75 stream flow. And here's the rigid wall. So you can see how uh, each group has the rigid wall between the simulate and observed one. Okay, I think let's go back where we are. Okay, it seems to be a little decreasing the pi and that's reach number 57 and 75. Yeah, it's done. So many worker is great. Yeah, while it's running, I will answer some of the questions in the chat first. Wow. Okay. We have a one questions. Number of workers should be limited. Number of cores. Um, not really, but you know the cores is always once you have more work to do with the cores, and the core speed is going to go down, right? And then it affects your optimization's time too. So I suggest, okay, let's say you have 10 parameters. There's no need to more than 20 workers because each iterations, 20 workers are going to work to find uh, the, the parameters, optimized parameters. Then during the partial parallelization of the lambda search, you may have like a 7 or 5. Yeah, this is the one I found out when we do journal approach. We have only two different parameters. It's really, once you set up like my minimum iteration number set maybe 30. Well, if PAST doesn't find any good solutions, they're going to just wrap it up and they give you PAST parameters they found, and it's going to stop. So let me just check it. Yeah, little just decreased up the pi, then that's all for this simple animus apex mod flow. I think I have 60 minutes. I did really, did really faster because of time. And then once we go to linear analysis, if we have a time, and then once we have covariance metrics of your parameters and observed noise, then there's lots of things we can do, like posterior uncertainties or prior uncertainty, uh, and parameter identifiabilities too. And I think I can show you this. Maybe top one. I included no. This one has been really interesting to me. This is the one of the parameter kind of composite sensitive analysis. You can see these color are the apex parameters, which is surface parameters. And then you can see this bar is how sensitive they are. And because we did categorized each parameters like a build or apex, and then this is the pilot point approach, and so you have like 100 different pilot point for specific yield, and then specific yield here, and this RC indicates your riverbed conductance, and this is RT indicates riverbed thickness, and we did, and is hydraulic conductivity, and I analyzed this. Sometimes I did only optimize the parameters on the stream flow and only optimized water table using these parameters. Also, sometimes I combined all of the hydrological responses like the stream flow and sediments and water table. And then now I see these parameters can really, visible to these different group of the observed data, like the sediments water table doesn't really are not sensitive this the riverbed thickness, but once we include this stream flow discharge as calibration targets, riverbed thickness is kind of the high um, sensitive coefficients, and they show you. And I think I really just went over really quick for these sessions, but I'm going to put up this. Well, you already have the access to this GitHub and the Apex MF Python package. So once you have more questions, and you can send me email or put any reports for the bugs sort of things. How do you interpret composite sensitivities? This is the composite sensitivity that comes from the Jacobian matrix. This is kind of local sensitivity analysis. While you calibrating past just putting all the differential delta value of your parameters and delta value your assimilate value. Then using the Jacobian matrix, they estimate the composite sensitivity analysis. And once you done your analysis, or while you done it, then your main past folder is going to have this sensitive analysis too. And each iterations have their different sensitive value. But this is not the global, and the global I think I show you through the webinar. Past global community. This is the suit called the past PP past plus plus sensitivity. Give first orders and second moment parameters global sensitivity analysis too. And if you know Python package, Python stream language, you can use the PyMu. And I'm trying to put it this functionalities into this Apex MF too. So Apex mode can be with Apex mode flow model. We can perform this global sensitive analysis. Any other questions? Yeah, once it's done, you can just close it. Your work is slave execution terminated by master. Yeah. what kind of the management optimizations? Like you're talking about crop optimizations? I think I put up here. Yeah. Oh, yes, honestly, that's water allocation optimization is not my field, and I had have to study more about that. But if you want to uh, work, and then I can collaborate with you, and then you have to teach me. Because all of the the past is the model independent model, so everything can be your parameters, but still we have to test it out. For the crop parameters, this is just recently worked with my colleague, and then he need to uh, put this crop farm and then see the crop ill optimizations. And here's crop debts, and this Apex MF Python package can read this top and the soybean, and they're going to change these parameters as well. And we are testing now. This is really, valuable data sets, for the crop data. And then I really want to test out these crop parameters for each crop types. And this is doable. This is already built. We have the functions. Once you want to optimize your crop parameters, we have the option is here, and then see the leap year index or something. And then let's see. Yep. So here's leap year index files, and the subbasins leap year for the leap year index. And yes, and then also we have also pilot point approach included. So based on the pilot point approach, you might have we might need additional geostatistical analysis, such as based on this pilot point approach, we have to interpolate your parameters and to the grid, and to interpolate there's lots of methods like a kriging, and the kriging method need variable model to see correlations between the points on your watersheds and to see the trends. So that's the one thing I usually put in the next webinar, and we can do pilot point approach. Jeff, would you like to have 5-minute break and then we can move on to Q&A session?